Thank you, and well, thank you to the organizers for inviting me to speak here. We're going to talk about an ongoing project I have with Francis Brown, Clement Dupont, and Javier Frezin, which will, as we'll see, has to do and is inspired in a way by physics. Um, okay, so just sorry. um, all right. So mainly we will be talking about periods, which are integrals of this shape, where omega is an algebraic differential form. So we have here P, a polynomial in x1 to xn, over Q, polynomial x1 to xn. It's an algebraic differential form on some algebraic variety x. And we integrate that over sigma, which is some n cycle on the complex points of that algebraic variety. Conjecturally, these types of integrals, periods have an action of an algebraic group over Q, which I will denote G mod, called the Motivic Galois group, and which acts on periods and preserves all algebraic relations. So we have an action of this type conjecturally, or dually, because this is an algebraic group. Dually, we have a coaction of an algebra of the Hopf algebra of functions on G mod. And that has a shape like this. So an integral is sent, an integral omega over sigma is sent to a finite sum of tensor products, where on the left we again have integrals of the same type tensored with AI, where AI is a function on G mod. Now, in order to so this is all based on some very deep conjectures in algebraic geometry. So in order to sidestep them, we're going to use cohomology. To an algebraic variety we started with, the x from before, we associate two vector spaces. One is the Betti homology of x, which is a Q vector space of n cycles on the complex points of x modulo boundaries, and H and de Rham X is a K vector space of algebraic n forms. So here we have closed n forms. D is just a standard differential. So we have closed n forms modulo exact forms. Okay? And what we're going to do is for an integral we started with, we're going to find an x such that the differential form in the integral generates a class in the algebraic de Rham cohomology of x. This is our H and here, and sigma generates a class in the Betti homology of x. So these two vector spaces have a perfect pairing given by the algebraic de Rham theorem, and this simply maps a class of sigma and a class of omega to the integral of omega over sigma. Right, so what we actually want is an unconditional coaction formula, that we can maybe study and compute something concretely. And to do this, we're going to introduce a ring of what we call motivic periods. This is simply going to be that to an integral omega over sigma, we're going to add the data of the cohomology of x. So we're going to find some x such that, as I said earlier, omega is in the de Rham cohomology of x, sigma is in the Betti homology of x, and we're going to add that data to this integral. And we're going to mod out by the obvious relations, Stokes bilinearity, change of variables, etc. The ring of motivic periods, it's a Q span of triples like this. Again, we should think of this thing within the square brackets here as the integral up here with the added data of the cohomology of x. It comes equipped with a period map, which just takes a triple like this and integrates omega over sigma. If Grothendieck's period conjecture is true, this map, this homomorphism of rings, should be injective. Okay, so the upshot of this, why are we doing this, is so that we can have an unconditional abstract formula for the coaction that we started with, which looks like this. So a triple, like this, as I said, the integral omega over sigma plus the data of the cohomology of x. This is sent to a finite sum of this of tensors, of simple tensors, where on the left we have the same type of triple where EI are some new differential forms now, tensored with some AI functions on the Motivic Galois group as we stated at the beginning. So EI here form a basis of differential forms for X. So they're a basis of this K vector space of that's the algebraic Durham cohomology of X. Right. Yes. Yeah. So I guess the conjecture is that whatever, yeah, that there are many different x's you can put here and so on to get the same complex number, you mean, or? Yes, exactly. So the point is that exactly, and the conjecture states. So, for example, 2 pi I is h1 of gm you put here, and you get you integrate dx over x over the path around 0. Of course, you can get it in many different ways. The point is that the conjecture claims that whichever way you get it, there is always a combination of these basic relations that gets you from, or equivalently, a geometric transformation of x into some other space that gets you an equivalence of these things. There's a geometric thing happening in the background that then allows you to. Yeah. So as I said, that's why square brackets there. It's an equivalence class, right? But crucially, you have this data of x, and this is exactly how. If we want to do so, when I say something is motivic, I mean we've proven it using the geometric transformations in the background. Yes. Mm-hmm. Oh well. It's bilinear in these in both of these. You can just add q linearly. You can add there's the cycles. You can wedge together forms and so on, right? Yeah. Well, yeah. So a priori, you just take the product of spaces here, and you just wedge everything together and add everything together. But then the claim is that, of course, that you could write this as a single. There's a third space. That's just you write this as a single integral over some third space and so on. It's a bit abstract here. Yes. Mm-hmm. 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 Unique in which sense? Right, there is one equivalence class, but of course there are many triples. So if I were to write these as triples without modding out by this, there are many different triples that lead to the same number. Right? So many different ways to write down the same complex. Yeah, that the right. Right. So I'm going to add I'm going to add the specific x here, and I'm going to work with that data. So rather than exactly. So in principle, I should be able to just work with these two, and everything in the background that happens should be algebraic. But this, I don't know this, so we're adding this data. Oops. So okay. So an example of the coaction. Erase the word multiple here. That was a mistake. This is an example with just single zeta values. So this is conjectural. So we have so for an action an element G in the Q points of G mod, the algebraic group that I call the Motivic Galois group. This G acts on a single zeta in this way, where lambda to the power n, G and A and G are rational numbers. The coaction would be, the equivalent coaction would be zeta n tensor lambda n. This is a function, as I said. So lambda n, I'm evaluating it at G here. So here, this is a function on G mod. And plus 1 tensor an is again a function on G mod. Unconditionally, this works unconditionally, but only for Motivic zeta values. Motivic zetas are these, again, these are some algebraic integrals, or yeah, these are some algebraic integrals with the associated data of the cohomology of some algebraic variety. Okay, so what does this have to do with physics? There's something called the cosmic Galois group, which comes from this idea that the action of G mod should be closed on the space of Feynman integrals. So, or equivalently, the coaction should always look something like this. So the coaction of a triple here, where G is a Feynman graph, and this omega G is the parametric Feynman integrand, sorry, where U and F are first and second semantic polynomials, and sigma G is just the standard simplex in projective n space. Right, so to this parametric integral, we lift this parametric integral to a triple like this, where Hg here is what we call the Feynman motive, which was defined by Francis Brown. And the coaction should then send a triple like this to a finite sum, where on the left-hand side we have again these motivic periods, but each of them is again a Feynman integral, really, with the additional data of this Feynman motive. Gi are some Feynman graphs that are somehow obtained from this original Feynman graph G. This is very vague for now. I'll get on with it, and we can talk about this some more. But the point is that all we have on the left-hand side here are Feynman graphs and Feynman integrals. That is their motivic versions, but still, that's the idea of the cosmic Galois group, and this leads to some constraints, some interesting constraints on the space of Feynman integrals. This goes by the name of small graph integral. I could talk more about this, but I kind of the motivation here is that, well, one way to see it, for example, is that. You can, for example, let's say that in your theory you know that a certain period doesn't appear, then by this principle, no period of which the original period you know is not there would be a conjugate of, under that coaction, that can't appear either. So you can exclude sort of infinitely many periods by excluding one, by this sort of principle. But there's a problem with the formula that I wrote earlier with the different Feynman integrals. That is, we need to include somehow regularization in this story. We can't just consider convergent Feynman integrals. So, I mean, that's obvious to a physics audience. So how do we do this? There was a conjecture by Abro, Brito, Dur, Gardi, and Matthew, which inspired this whole thing. And it basically says, and I'm slightly paraphrasing, but it basically says coaction is compatible with dimensional regularization and can be made diagrammatic. So the goal now will be to kind of formulate this mathematically and provide a partial answer to this. Okay, so let's step back once again and consider general algebraic Mellin transforms. What do I mean by this? We still have x over k in algebraic variety. We have a bunch of algebraic functions on x, f, f1, fn, from x to gm invertible, omega an algebraic differential form on x, and sigma a cycle on the complex points. Potentially, we can add boundaries to everything here, but for simplicity, I'm just using x without any divisor in it for now. In any case, what we want is a coaction, some version of a coaction for integrals of this shape. Integral of f to the power s omega integrated over sigma. And in fact, we can now expand this around s equals 0 and get a power series like this, where each coefficient of s to n here is a classical period. How is this a classical period? You rewrite the powers of logs of f as iterated integrals, and basically putting these things together gives you periods, again, in the classical sense. I'm not going to discuss the details of that, but the point is these are classical periods, so these carry the action of G mod from earlier. And we want to somehow put that together into some sort of an action for this, if that makes sense. More generally, we'd like to consider sort of multiple functions f, like this. I'm just going to focus on one, but basically everything I say works with more than one. let's look at an example. So the beta function, here the big N is 2. We have two functions, x and 1 minus x, from p1 minus 0, 1 infinity to gm. And we look at this, integral, and this has an expansion of this shape. Crucially, in the coefficients of s and t in this expansion are single zeta values. Let's just ad hoc lift these single zetas to Motivic zetas to define this beta Motivic here. It's just replacing zetas with their Motivic versions. And to each Motivic zeta in this expansion, we will apply the term-by-term coaction which we had seen before, this formula we've seen before. So a priori, we get a power series in S and T with coefficients in this tensor product here. What do I mean by this? I just want to make sure I get this point across. So what I mean is I have a power series where I have Motivic periods, something like Motivic periods of sort of K1, K2, SK1, TK2. These psi's are just Motivic periods, and if I apply term by term delta, I will get a sum of sigma Motivic K1, K2 plus some other index I, for example, tensor AI, and then S of K1, T of K2. Right? So this is an infinite, this is just an infinite, this is a series, this is a power series. And we'll see what happens. Something very interesting happens, actually. If we also scale S and T in this previous expression, so I coact, I plug in this into here, I get an infinite series, and then I also scale S and T by lambda to the minus 1. Lambda is the same lambda that appeared earlier in the coaction of the zeta. I can rewrite this power series as a product of two power series, where on the left-hand side, we only have as coefficients Motivic periods, and on the right-hand side, we only have these functions on G mod. So basically, instead of having an infinite series like this, I can write it as a sum of some new Motivic periods here, K1, K2 tensored with, SK1, TK2, the whole thing tensored with another series where here I have the AI from earlier, and then again K1, S and T, K1, K2. Sorry, this is a bit of a mess, but the point is that I can factor that formula like so. So instead of delta of beta Motivic being in this ring of power series in S and T with coefficients in this tensor product, we actually have that delta of the beta Motivic is in the tensor product of power series with coefficients in just Motivic periods with tensored with power series in S and T with coefficients which are functions on the Motivic Galois group. In terms of the group, we can rewrite this coaction in terms of the group action and get an expression like this. This is similar to what I've done with the Motivic zetas. I'm sorry? Yeah. Yes. Yeah, they're the same ones that appear in just a single zeta. Exactly. And so, if I evaluate them at a given G, which is in a Q point of G mod, I will get that this expression is a power series. It's a quotient of two power series in S and T. Okay, so the point is that this holds generally. The main theorem is that let EIS be a Taylor expansion of an algebraic Mellin transform of F, and let G be a K point of G mod. Then G acts on the power series EIS. In this way, it just gives a finite sum of where on the right-hand side we have, again, similarly, expansions of algebraic Mellin transforms. Now for omega n, some other differential form, algebraic differential forms. And here we have simply the elements of K double bracket S. As a coaction, I can write this as a coaction simply by saying that that EIS is a finite sum 1 to n of EIN S tensored with ANS. Okay, and so these here are in O of G mod double bracket S. Okay. So this is surprising because it's a finite formula for the coaction of infinitely many periods. Because in here I have infinitely many Motivic periods. It's a power series, and yet it gives. We can write down the coaction in a finite way. Okay, sorry. The slogan, which is, I guess, these slogans are the only thing that should be taken from this talk, is that the Motivic Galois group acts on Taylor expansions of algebraic Mellin transforms via power series. Via power series, I mean with coefficients in power series like this. Okay, back to physics. Let's start with a Feynman integral, but in dimensional regularization now. We add...
So the capital N is the Feynman.
Yes.
And in that formula, these functions so that you know all
Yeah.
AN.
So n was 1.
N was just 1.
N was just 1. I have a rank 2 example, but I don't think I have time. Yeah, so n was 1 in that case. Okay, so now we have for G a Feynman graph. Let's consider the dimensionally regularized Feynman graph, Feynman integral associated to G. So we just add the parameter epsilon here to this quotient. This G should be a normal G, not a curly G. And we expand around epsilon equals 0, and we get this sort of expression. Now the f that we had earlier in general, the f is now this quotient of two graph polynomials with the appropriate powers to make it homogeneous. A part of the conjecture of the authors I mentioned earlier is that the coaction of EIG epsilon should be expressible in such a way that on the left-hand side we have the same types of expansions, i.e. dimensionally regularized Feynman integrals of some Gn. These Gn are some graphs related to G, tensored with some power series in epsilon, where the coefficients are functions on that Motivic Galois group. So this here is a general thing, and we know that works. What we want now is a much more constrained situation where I is a Feynman integral, and then the claim is that on the right-hand side we will get these INs, which will also be Feynman integrals, and hopefully we can also relate them somehow to the one we started with and so on. So, okay. So in any case, as vaguely as I've stated it here, this conjecture is true. That's the first thing. Now, I'm not going to avoid subtleties, I will mention them. But this is already something. What are the subtleties here? How do you get these GNs? I give you G, how do I get the GNs? Well, we know already, this is going to be part of the theorem, that it will be enough to consider subquotients of G. You start with a graph like this, and you only consider bubbles and, I don't know, things like this and so on, right? We will also need to consider dots on graphs, by which I mean just adding dots on propagators. And there will be some constraint on how many dots you need and so on in order to write down this formula. There will be space for improvement, though. There is a deeper question, which is how do you think about this power series with coefficients in these functions on G mod? And the suggestion by Abro, Brito, Durgardi, and Matthew is that these should be somehow related to cut graphs. This is difficult for various reasons. I'm happy to discuss after the talk. But in any case, it's a very interesting conjecture. So let's talk a little bit about why this holds. Let me see how much okay, yeah. Another slogan, so the previous one was The Motivic Galois group acts on Taylor expansions of algebraic Mellin transforms through power series. This is the second one I'd like you to take away, is that the Motivic coaction on an algebraic Mellin transform is controlled by twisted cohomology. Again, bit vague, because which twisted cohomology? Okay, let us fix a generic complex number S0, by generic I mean non-integer, and consider this type of integral, omega f to the S0 sigma. So I've specified that S from the beginning to be some complex number S0, some complex number S0. To make sense of this integral, for each point of sigma, we need a determination of f to the power S0. This is in mathematics, we just call this information a local system. So this is encoded by a local system, curly 0. And again, we want to make sense of this cohomologically in order to sort of add the geometry into the picture. How do we do this? Well, we replace the Betti homology from earlier with what's called Betti homology with local coefficients in this local system ls to the power 0. So instead of just n cycles on x, now we want to consider n cycles with the choice of branch of f to the s0 at each point of that given cycle. The de Rham side, i.e. the differential forms side, will replace the algebraic differential forms with, well, with this. It's another k-vector space where we now have, well, closed differential forms under the nabla S0, which is this connection form here. So we twist, so instead of just the d, we twist by this factor s df over f here. And again, it's just the n forms which vanish under nabla S0 over the exact forms under nabla S0. Deligne tells us that there is a perfect pairing in this setting, which exactly gives us integrals of this shape that we're interested in. So to sigma and fs0, by this I mean the choice of branch at each point of sigma, and omega, we associate this integral. And it's a perfect pairing. Lovely. In physics, this has been used and lots of people seem interested in this. For example, nabla 0, omega equals 0 encodes IBP relations. The basis of what I call the twisted de Rham cohomology of X would be something you would call a basis of master integrands. You get intersection pairings and so on. And many people have been working on things both with respect to Feynman integrals and string theory. Oops. Problem. We want to relate some notion of a coaction on the coefficients of the twisted cohomology pairing, i.e. of integrals of this shape, to the coaction of classical periods appearing in this expansion. Okay? So these are classical periods, as I said, so they're acted on by Gmod. We somehow want to relate that to some notion of a coaction for this. But on the level of cohomology, this makes no sense, because the cohomology groups with local coefficients like this have nothing to do with classical cohomology groups for any y, unless S0 is a rational number. I can explain how they're related when S0 is a rational number. Okay, another problem, very obviously, if we fix S0 to be a complex number, we're not allowed to expand around some value of S, right? Okay, so how do we get around this? So just bear with me with this slide. Let me just see. Oh, wow, excellent. Well, we want to introduce a sort of a formal local version of twisted cohomology. We want some cohomology groups which will encode those expansions on their own. So we want these expansions where the coefficients are motivic periods. We want some sort of cohomology group such that we can have a perfect pairing that spits out things like this. And what we do is we use this projective limit here. So basically, okay, so on the inside, let's see what we have. Classes in Hn of this here, these are just represented by polynomials of degree less than or equal to d in S, where coefficients are algebraic differential forms on X. And these polynomials should be sent to 0 by nabla S, modulo the exact versions of those. So, so basically what I'm saying is, I mean, one should think of this projective limit here thing is, you know, it's the same thing as how you would take rings of polynomials up to a certain up to a certain degree and put them together to form the ring of power series. That's the concept of a projective limit, except here we have these polynomials where the coefficients are algebraic differential forms on X. Key technical point, which I'm not hoping many people will remember, is that, what I'm doing here is putting together these objects which are motivic, by which I mean they come from geometry. They come from something called the motivic fundamental group of GM, and the periods of this thing are powers of log T. These are exactly the things that appear in our expansions that we're interested in. So we started with these expansions of if we expand f to the s, we get logs of all the powers of logs of f. We have to encode that somehow, and basically, if one thinks really hard about it, this is the way to do that. And in particular, it also leads to the parameter s as being understood not as something just formal. It's actually a generator of the dual of the de Rham cohomology of GM. So it's the dual of dx over x, basically, and that explains why it has to be scaled by lambda to the -1. Lambda is still the same lambda that appears in the coaction of the single zeta. There's a corresponding Betti version, and the perfect pairing is valued in Laurent series S. Actually, yeah, I've gone fairly quickly, so I'll have the time to do the rank 2 example, maybe, if we can lift this thing. In any case, let's look at an overview picture of what we said so far. We've only actually in this talk talked about the bottom row of this diagram here. Namely, we talked about these types of expansions, which are encoded by this thing that I call the formal local twisted cohomology. These objects Mn, de Rham, Xf. We have also talked about traditional twisted cohomology. By traditional, I'm saying traditional because lots of people have been working on this, from the Japanese school to all of these people in physics and so on. And the point is that what was kind of required was how does one go from some sort of a formal cohomology on formal coaction on this to a coaction on the coefficients appearing here, which are these classical periods. And the answer to that is one introduces a third category. These are by the way 2 different categories. It doesn't really matter. One introduces a third concept which I call Mellin motives, and these are basically this is formal global twisted cohomology. Here we have as sort of coefficients of those comparisons that we've seen in 2 cases before. We have integrals of this shape, where s is really a formal parameter. So this is a function of s. It's not a fixed complex number. It's not an expansion around s equals 0. It's really a formal parameter. And from here, we have 2 operations. We can expand around s equals 0 in this case, or we can specialize s to s in C. So this is really how these 2, they're both sort of shadows of something that sits above them. And this is not a part of this discussion, but it's a very interesting thing to study, these global Mellin motives. They're they're just called Mellin motives. They're global in this sense that they're not expansions. That's what I mean. These are the correct setting to consider difference equations of algebraic Mellin transforms. They're related to the algebraic Mellin transform of D modules in the sense of Lozère and Sabat. In particular, the de Rham realization is a Mellin transform of a D module in that sense. This has also been proved by now, and so this is something that will come later. Yeah. So basically, that's what I wanted to say about those. I have about 5 minutes left, so I can either, if you have questions about these so far, or I can give that rank 2 example. Audience choice.
So I suggest we thank Matija first.
Okay.
What I suggested though is take some questions now and see how long does it take, and then we can because if we need the slides to answer them, then let's keep them here. So if there's any question, yes.
Thanks a lot for the very exciting talk. I have a very naive question. So I think, well, long time ago when people was playing around with sector decomposition, they always say I subtract some terms from the finite integral. And then for the integrand level, I do this kind of epsilon expansion to make sure every step I get a finite answer. But for your expression, it seems that you have some technology to directly do this kind of expansion or redefine this kind of expansion in epsilon for finite integral. Is that true?
Okay, so I don't understand. So what was the question? So I guess the broad question is, how does renormalization play with all of this, or something like that?
Do you need some way like sector decomposition to subtract some terms first,
right,
and
okay.
then
No,
safely do this
so
kind of epsilon expansion?
Right. Okay, so one thing I made a mistake. I keep calling them Taylor series. It can be Laurent series. It doesn't matter. Like in fact, in the beta example, one gets 1 over s and 1 over t and so on. So yeah, these don't have to start with k bigger than or equal to 0. You can start with negative powers.
Yeah, but even with negative powers, still this situation is quite tricky for finite integrals. Still, sometimes you need to first subtract some terms and then do this kind of expansion, because possibly this kind of expansion, well, it's not commutative with this kind of finite integral evaluation. That's a sector decomposition, isn't it?
I'm afraid. Yeah, so okay, blowups are not shouldn't be a problem in this setting. So, for example, for the beta function, right? For the beta example, you don't have the endpoint 0 and 1 are not in the space. We have p1 minus. So the appropriate cohomology group. I'm running out of space here, but the appropriate we consider this sort of thing for the beta example. And then we just have endpoints be, we consider the integral, the path sigma is really the path literally the path from 0 to 1. Even though these things are excluded. That's because there's this thing called compactly supported cohomology. We have a regularization method built into this, basically. This path is considered as a locally finite path, meaning the closer you get to 0 or to 1, you get shorter and shorter segments, but any sort of open inside here will intersect finitely many of them, that sort of thing. So regularization is sort of built in for these types of things.
Just curious about, so in the case of like when you set d equals to 4 or 2 or something like that, you studied the elliptic sunrise. So as soon as you add epsilon, you think that all of these coaction conjectures just go through, or are there still some problems and subtleties?
Yeah,
So
the
just
coaction,
maybe.
you can write down the coaction of the sunrise. What you would get is, I can't remember now. Okay, so as conjugates, you would get you would get sort of the dim-reg versions of 4 things with dots on them, like this. I don't know. I can't remember now which ones, but 4 of these, and I have no idea. Something like that. That would be one, and then you would get betas associated to these things, to these quotients. You would have so if you started with the sunrise.
I guess the question is
Yeah, that can stay there.
in the elliptic case, if you have a problem with
What's the problem? Yeah.
So when you go to higher genus, you have a problem with interpreting the right-hand side as an integral.
Oh, okay, yes.
Left side I'm twisting, does this problem go away, persist?
It persists, absolutely. Yeah. So the question of interpreting this side as something to do with Feynman graphs. This is what I said in the coaction, or in the coaction conjecture that I mentioned, of some who are here. This is the diagrammatic part. So it should be diagrammatic. I don't see how to do that higher in more than one loop, because there is a sort of there's some problems with some choices. You need to make some choices, and it's not clear how to make those choices canonically. It's not solved by this.
Any more questions? Maybe I have one. So this is tied to Feynman diagrams, really, but we know that in many theories, when you add Feynman diagrams together, there are some simplifications. Is there a way to do these things for like full amplitude, for example, in one go?
No, we haven't thought about that. It would be interesting to think about that, but I'm not sure how to do that. I see what you mean though.
Okay, thanks.
Sorry.
I suggest that we stop here, and if somebody wants to stay and talk to Matija about the rank 2 example, then you are welcome to do that, but let's thank Matija once more.